Hikers enter clear skies. Minutes later, the weather turns violent without warning. Fog walls rise. Temperatures crash. Visibility vanishes. Then people disappear. No storms on the forecast. No alerts. No time to escape. Search teams arrive to calm conditions and empty trails. The same sudden weather shifts appear again and again in missing person cases. Why does it change so fast in these locations? What triggers it, and why does it always come right before someone vanishes? Weather that did not behave as expected. On the 9th of January 2018, lake effect snow formed along the southern shore of Lake Erie. Narrow bands of heavy snowfall developed over northwestern Pennsylvania and western New York. Radar data from the National Weather Service showed sharply defined corridors of intense precipitation separated by areas of clear air. Wind direction shifted repeatedly across the lake surface. Along sections of Interstate 90 and Route 5, visibility changed within minutes. Erie County police reports document an increase in abandoned vehicles and traffic incidents during the afternoon. Emergency dispatch records list multiple calls related to sudden whiteout conditions. In official documentation, weather is usually recorded as environmental context. Temperature, wind speed, snowfall totals, and visibility are entered alongside timestamps and locations. When a disappearance occurs, these details are preserved in the same format. The structure remains technical and neutral. One of the most thoroughly documented weather disasters in the United States occurred in February 1978. Beginning on February 6, the blizzard of 1978 affected New England and parts of the mid-Atlantic. Massachusetts, Rhode Island, and Connecticut experienced prolonged snowfall, hurricane-force winds, and coastal flooding. Snowfall exceeded 30 inches in several communities. Wind gusts surpassed 70 miles per hour. Visibility dropped to near zero for extended periods. During the storm, thousands of vehicles were stranded on highways. Some motorists left their cars in an attempt to reach shelter. State police and National Guard records show that multiple missing person reports were filed during and immediately after the blizzard. Several individuals were located days later in areas that had been inaccessible. Others were found deceased. NOAA archives and state emergency management reports confirmed that weather conditions severely restricted rescue operations. In February 1979, 5 men from Yuba City, California disappeared after attending a basketball game at California State University, Chico. The group, later known as the Yuba County Five, drove east toward the Plumas National Forest. Their car was found abandoned on a mountain road near the Oroville-Quincy Highway. The vehicle was operable and not stuck. Weather records from nearby stations show freezing temperatures and snowfall in higher elevations during that period. Snowdrifts covered parts of the roadway. Search efforts were slowed by winter conditions and rugged terrain. Over the following months, 4 of the 5 men were found deceased in forested areas and a remote cabin. 1. Gary Mathias was never located. Law enforcement files, newspaper archives, and meteorological data remain publicly accessible. In July 1996, a German family became lost in Death Valley National Park. Tom Mahood, Cornelia Mahood, and her brother Georgie Reichert drove off paved roads while attempting to find an alternate route. The area was experiencing extreme summer heat. Furnace Creek Weather Station data shows temperatures exceeding 120 degrees Fahrenheit during that week. After the family failed to return, park authorities initiated search operations. Their vehicle was found in a remote desert location. Over the following years, human remains and personal belongings were discovered at different sites. National Park Service investigations and German police records cite dehydration and heat exposure as primary environmental factors. The case has been documented in official reports and international media coverage. In June 1969, 6-year-old Dennis Martin disappeared in Great Smoky Mountains National Park in Tennessee. He was last seen near Spence Field during a family hike. A sudden thunderstorm moved through the area shortly after his disappearance. Rain, fog, and falling temperatures affected visibility. National Weather Service data and park records confirmed deteriorating conditions. Search teams, including park rangers, military personnel, and volunteers, were deployed. Weather repeatedly interrupted operations. Flooded streams and low visibility limited access to certain areas. Despite extensive searches, Martin was never found. The case remains one of the most studied missing person incidents in U.S. national parks. Maritime environments also provide detailed documentation of weather-related losses. On the 11th of February 2017, the fishing vessel Destination sank in the Bering Sea. All 6 crew members were lost. A United States Coast Guard investigation found that the vessel encountered freezing spray, high seas, and strong winds. Ice accumulation increased weight and reduced stability. Weather buoy data and satellite imagery confirm hazardous conditions at the time. The Coast Guard report states that rescue operations were limited by visibility, wave height, and ice buildup. The investigation remains publicly available. Historical records show similar patterns. During the Dust Bowl era of the 1930s, severe dust storms affected large parts of the Great Plains. On the 14th of April, 1935, known as Black Sunday, a massive dust storm swept across Oklahoma, Kansas, and Texas. Visibility dropped to near zero. Wind speeds exceeded 60 miles per hour. Weather Bureau reports documented unprecedented airborne dust concentrations. Newspaper archives from the period describe travelers and farmers reported missing during major storms. Some were later found disoriented or injured. Others were never located. Weather and disappearance notices appear together in regional records, often without additional analysis. In July 2021, extreme rainfall caused catastrophic flooding in western Germany and eastern Belgium. Rivers including the Aar and Erft overflowed after record-breaking precipitation. Some areas received more than 150 millimeters of rain within 24 hours. European meteorological agencies confirmed that these totals exceeded historical records. More than 180 people died and dozens were reported missing for weeks. Emergency management agencies noted that floodwaters rose faster than warning systems anticipated. Weather station data, river gauge measurements, and satellite imagery are publicly accessible. Investigative reports focus on response timing and infrastructure failure, with meteorological data forming a central reference. Advances in monitoring technology have expanded data collection. Doppler radar, automated weather stations, and satellite systems now provide continuous coverage. Despite this, localized variations remain difficult to predict. Mountain terrain, desert basins, and coastal zones continue to produce rapid shifts that appear in records as short-term anomalies. Search and rescue documentation reflects this uncertainty. After-action reports list snow depth, rainfall totals, wind chill, and heat index values. They describe operational delays caused by storms, fog, flooding, or extreme temperatures. Personal behavior is rarely analyzed. The language remains procedural. Climate research institutions publish long-term studies on changing weather patterns and increased variability. These studies rely on aggregated datasets and statistical models. Individual disappearance cases are not part of their scope. Local and federal agencies continue to use standardized reporting formats. Over time, this has produced extensive archives in which meteorological data and missing person records exist side by side. A blizzard develops, heat intensifies, floodwaters rise. In the same period, someone is last seen. The documentation records both elements without interpretation. Files remain active until evidence is found or investigations are closed. Weather records remain permanent. Missing person reports remain searchable. Both persist in neutral language, unchanged by time. Sudden shifts recorded without explanation. In western North Carolina and eastern Tennessee, emergency agencies reported that conditions deteriorated faster than predicted. Roads that were passable in the morning became impassable by early afternoon. Visibility declined sharply. Search and rescue teams responding to stranded motorists documented sudden temperature drops and near zero visibility. NOAA archives show that several monitoring stations recorded major shifts within periods of less than 2 hours. These rapid transitions appear repeatedly in historical weather records. Forecast discussions often reference unexpected intensification or unanticipated track changes. The terminology remains technical and restrained. The impact is described through measurements rather than narrative. On the 13th of March 1993, a massive storm system moved up the eastern coast of the United States. Later known as the Storm of the Century, it affected areas from Cuba to eastern Canada. Along the Appalachian Mountains, snow, sleet, and freezing rain developed within hours. Wind speeds exceeded 50 miles per hour in some locations. Barometric pressure dropped rapidly. National Weather Service stations recorded changes that exceeded most forecast models available at the time. In April 2011, a series of powerful tornado outbreaks affected the southeastern United States. Between April 25 and April 28, more than 300 tornadoes were confirmed. Weather stations recorded unstable atmospheric conditions, extreme wind shear, and rapidly forming storm cells. Forecast models identified the risk, but the speed of development exceeded early projections. During the April 27 outbreak in Alabama, storm cells formed and strengthened within minutes. Emergency management reports note that sirens in several towns activated only shortly before impact. In rural areas, communication was delayed. Some residents were reported missing in the immediate aftermath. Weather data shows that storm intensity escalated faster than anticipated by short-term forecasts. In mountainous regions, rapid changes are frequently documented. On the 7th of September 2003, a powerful storm system moved through the presidential range in New Hampshire. Mount Washington Observatory recorded wind speeds exceeding 100 miles per hour and temperatures below freezing. Clouds descended quickly over hiking routes. Visibility dropped to near zero. That day, several hikers required emergency assistance. Rescue teams noted that conditions shifted from mild to hazardous within a short time window. Weather station logs show steep pressure changes and sudden temperature drops. The event is frequently cited in meteorological studies of rapid alpine weather transitions. Desert environments also produce abrupt atmospheric changes. On the 15th of August 2012, a monsoon storm developed over northern Arizona. Within hours, intense rainfall caused flash flooding in parts of Grand Canyon National Park. Weather radar showed stationary storm cells releasing heavy precipitation. River gauges recorded sharp water level increases. 20 hikers were swept into Havasu Creek. 11 were killed. Emergency agencies later reported that rainfall totals exceeded short-term forecasts. Meteorological summaries described the storm as highly localized and difficult to model in advance. Similar patterns were observed in Utah in September 2015. A slow-moving storm system produced flash floods in Zion National Park. Rainfall accumulated rapidly in narrow canyons. Stream gauges showed water levels rising within minutes. Search and rescue teams responded to multiple emergency calls. Weather Service reports stated that the storm developed over limited geographic areas, reducing early detection. Radar data shows that precipitation intensity increased sharply over short time intervals. Forecast models had indicated rain but did not project the magnitude. Cold weather transitions appear in northern regions. In January 2014, a polar vortex event affected much of the central and eastern United States. Temperatures dropped rapidly across the Midwest. In parts of Minnesota and North Dakota, wind chill values fell below -50 degrees Fahrenheit. Weather stations documented temperature declines of more than 30 degrees within several hours. Transportation departments reported road closures due to ice formation. Emergency services noted that exposure incidents increased as conditions shifted faster than expected. National Weather Service summaries emphasize the unusual speed of the temperature drop. Coastal areas record similar phenomena. On the 29th of November 2018, a powerful bomb cyclone developed off the Pacific Northwest. Atmospheric pressure dropped more than 24 millibars in 24 hours. The system intensified rapidly. Wind speeds increased along the Oregon and Washington coasts. Seas became hazardous. Weather buoys and coastal stations recorded abrupt changes in wave height and wind direction. Fishing vessels and cargo ships reported dangerous conditions developing within short time frames. Forecast discussions later noted that intensification exceeded early projections. In July 2022, eastern Kentucky experienced severe flooding after prolonged rainfall. Several storm systems stalled over the region. Radar data shows repeated bands of heavy precipitation. River gauges registered rapid rises. Some waterways increased by more than 10 feet in hours. Weather Service reports indicated that soil saturation and terrain amplified runoff. Forecast models had predicted heavy rain, but localized accumulation exceeded expectations. Emergency agencies reported limited warning time in some communities. High-altitude environments produced distinct patterns. In June 1994, climbers on Denali encountered rapidly worsening weather. Wind speeds increased sharply. Temperatures dropped. Cloud cover reduced visibility. National Park Service records show that storm conditions developed faster than predicted. Rescue teams later reported that forecast windows closed earlier than expected. Weather station data from Kahiltna Glacier and surrounding areas shows sudden pressure and temperature changes during that period. Technological improvements have expanded observational capacity. Doppler radar can detect storm rotation. Satellites provide cloud and moisture measurements. Automated stations transmit data continuously. Despite these tools, short-term variability remains difficult to model precisely. Meteorological research papers frequently address this limitation. Studies published by NOAA and university research centers describe subgrid scale variability and rapid cyclogenesis. These terms refer to changes that occur faster than large-scale models can. Resolve. The language remains technical and focused on measurement. Operational forecasts are updated regularly, often every few hours. However, some events evolve between updates. In such cases, station data may reflect conditions that differ significantly from earlier projections. Incident reports from emergency agencies often include references to unexpected deterioration or rapid onset. Search and rescue documentation reflects these constraints. After-action reports list timestamps showing when weather changed relative to deployment. Delays are attributed to wind, ice, flooding, or reduced visibility. Forecast accuracy is not evaluated in these documents. The focus remains on logistical outcomes. Climate researchers note that increased atmospheric energy can contribute to faster storm development. Peer-reviewed studies analyze long-term trends in storm intensity and frequency. These analyses rely on decades of data. They do not focus on individual incidents. Local agencies continue to rely on short-range forecasts and real-time observations. Dispatch logs, ranger reports, and maritime advisories reference weather station readings. These numbers are recorded alongside coordinates and time markers. Interpretive language is minimal. Over time, databases accumulate entries showing similar patterns. Pressure drops, wind shifts, rain bands stall, temperature gradients sharpen. Within narrow timeframes, conditions change. Response systems adapt when possible. In some cases, adaptation is delayed. The records remain consistent in tone, measurements are preserved, timelines are maintained, explanations are limited to technical terminology. Sudden shifts are documented as deviations from projected ranges, not as narrative events. As monitoring networks expand, more data points become available. Yet, the fundamental challenge remains. Short-term atmospheric behavior continues to produce rapid transitions that appear in official logs as brief, measurable deviations. These deviations are archived alongside emergency reports and operational summaries. They remain part of permanent records. No additional meaning is assigned. Forecast models and their limits. In October 2012, weather prediction centers in the United States and Europe began monitoring a tropical system forming in the Caribbean Sea. The storm, later named Hurricane Sandy, moved northward through the western Atlantic. Early forecast models showed a range of possible tracks. Some projected a turn out to sea, others suggested a westward shift toward the northeastern United States. By October 25, several major forecasting systems began converging on an unusual scenario. The storm was expected to curve sharply toward the coast under the influence of a blocking high-pressure system over Greenland. This type of interaction was uncommon. Forecasters described it as statistically rare. Model outputs were updated every 6 hours as new data became available. On October 29th, Sandy made landfall near Atlantic City, New Jersey. Wind, storm surge, and rainfall affected large parts of the East Coast. Post-storm analyses showed that while some models had identified the unusual track early, others continued to display divergent outcomes until shortly before landfall. Technical reviews published by NOAA and academic institutions focused on how atmospheric blocking patterns were represented in simulations. Forecast models rely on mathematical equations that describe fluid motion, heat transfer, and moisture behavior. These equations are applied across a three-dimensional grid covering the atmosphere. Each grid cell represents an average of conditions within a defined space. Smaller scale processes must be estimated rather than directly calculated. This limitation becomes more visible during rapidly evolving systems. In October 2018, Hurricane Michael intensified quickly as it approached the Gulf Coast. On October 8th, Michael was classified as a tropical storm. By October 10, it had strengthened into a Category 5 hurricane before making landfall in Florida. Weather reconnaissance aircraft recorded falling pressure and rising wind speeds at a rate exceeding most model projections. Forecast updates were issued repeatedly in the final 48 hours. Post-event reviews found that ocean heat content and atmospheric stability were underestimated in some simulations. These factors contributed to faster than expected strengthening. Cold weather forecasting presents different challenges. In February 2021, a prolonged Arctic outbreak affected much of the central and southern United States. Temperatures dropped sharply across Texas and neighboring states. Power generation systems failed as demand increased and infrastructure froze. Days before the event, forecast models predicted cold conditions but varied in their estimates of duration and severity. Some simulations suggested a short-lived cold snap. Others indicated a longer event. Subsequent analysis by the Electric Reliability Council of Texas and federal agencies showed that the persistence of the cold air mass was not fully captured by several operational models. Weather models also face limitations in mountainous terrain. On the 24th of June 1994, a storm system developed over the Alaska Range. Climbers on Denali encountered rapidly deteriorating conditions. Wind speeds increased and temperatures fell. Snowfall intensified. National Park Service records show that weather windows closed earlier than expected. Meteorological stations in the region recorded pressure drops and wind shifts that developed within hours. Forecast models had identified a storm, but underestimated its speed and intensity. Later studies cited sparse observation coverage and complex terrain effects as contributing factors. In arid regions, rainfall prediction remains difficult. On the 14th of September 2015, intense rainfall triggered flash flooding in Zion National Park, Utah. Narrow canyons filled rapidly. Several visitors were swept away. Weather radar detected strong precipitation cells, but their slow movement and concentration were not fully anticipated. Post-event reports by the National Weather Service noted that the storm produced rainfall rates exceeding short-term model projections. The localized nature of the event reduced early detection. Similar findings appear in analyses of flash floods in Arizona, New Mexico, and Nevada. Forecast uncertainty is formally measured using ensemble systems. These systems run multiple versions of a model with slightly different starting conditions. The results are compared to estimate possible outcomes. A wide spread among simulations indicates greater uncertainty. During the March 2019 Midwest floods, ensemble forecasts showed large variability in predicted rainfall and snowmelt contributions. Rivers, including the Missouri and Mississippi, rose rapidly. Some levees failed. After-action reviews found that while flood risk had been identified, timing and peak levels varied widely among model runs. Atmospheric rivers present another modeling challenge. These narrow corridors of moisture can transport large volumes of water vapor from the tropics to mid-latitudes. In January 2023, a series of atmospheric rivers affected California. Heavy rainfall caused flooding, landslides, and infrastructure damage. Forecast models detected the incoming systems several days in advance. However, rainfall totals and impact zones shifted with each update. Studies by the Scripps Institution of Oceanography and NOAA emphasized difficulties in resolving moisture, transport, and terrain interaction at fine scales. Numerical weather prediction depends on initial conditions. Observations from satellites, weather balloons, aircraft, and surface stations are combined to create starting datasets. Errors in these inputs can propagate through simulations. In regions with limited observation networks, uncertainty increases. Parts of the Arctic, Central Africa, and the Southern Oceans have sparse coverage. Forecast models in these areas rely more heavily on satellite data, which may have lower resolution for certain variables. During the 2014 Malaysian Airlines Flight 370 search in the Southern Indian Ocean, Ocean and atmospheric models were used to estimate debris drift. Subsequent reviews found that uncertainties in wind and current forecasts affected search area calculations. Although primarily an oceanographic case, it illustrated how atmospheric modeling limitations influence operational decisions. Short-term forecasts, known as nowcasts, attempt to address rapid changes. These systems rely heavily on real-time radar and satellite data. They are designed for periods of up to 6 hours. Nowcasting has improved detection of thunderstorms and heavy rainfall, but remains limited for complex terrain and fast-moving fronts. In May 2013, a tornado struck Moore, Oklahoma. Forecasts had indicated severe weather potential. However, storm development and track adjustments occurred within short timeframes. Post-event reviews by the National Weather Service discussed challenges in communicating rapidly changing risks based on evolving model outputs. Model resolution continues to improve. Modern global models operate with grid spacing of less than 15 kilometers. Regional models use even finer grids. Increased resolution allows better representation of terrain and storm structure. It also increases computational demands. Research centers routinely test new model versions. These are compared against historical events and real-time observations. Performance metrics focus on temperature, precipitation, wind, and pressure accuracy. Improvement is incremental. Despite technological advances, forecast bulletins continue to include probability ranges and confidence levels. Wording such as likely, possible, and uncertain reflects statistical assessment rather than narrative interpretation. These terms are standardized in operational guidelines. Emergency agencies use forecast information alongside local observations. Dispatch logs, ranger reports, and transportation advisories reference model outputs and station readings. When conditions change quickly, updates are issued. Delays are documented without assigning cause beyond technical factors. Academic literature consistently emphasizes that models represent approximations of physical systems. Atmospheric behavior involves interactions across multiple scales, from global circulation to local turbulence. Some processes remain difficult to parameterize accurately. As datasets grow and computing power expands, forecast skill continues to improve. Long-term verification studies show gradual gains in accuracy. However, short-term variability remains a persistent feature of operational meteorology. Forecast models remain central tools in weather prediction. Their outputs shape advisories, warnings, and response planning. At the same time, technical limitations are acknowledged in internal reviews and scientific publications. The documentation of these limits appears in technical reports, training materials, and evaluation summaries. It remains consistent in tone. Performance is measured numerically. Uncertainty is expressed statistically. Interpretive language is minimal. These records form the basis for ongoing development. Each event contributes additional data. Each discrepancy is analyzed. The process continues without final resolution. Warnings that arrived after conditions changed. Radar operators at the National Weather Service office in Springfield, Missouri, monitored a rapidly organizing storm system as it moved across southwestern Missouri in late May 2011. Earlier forecast discussions had identified favorable conditions for severe thunderstorms. Atmospheric instability was increasing. Wind shear values were elevated. Satellite imagery showed expanding cloud tops. By late afternoon, radar signatures indicated strong rotation within several storm cells approaching populated areas. Tornado watches had been issued earlier in the day. As storm structure intensified, warning thresholds were met. A tornado warning for Jasper County was transmitted shortly before a large tornado entered Joplin. Sirens activated across the city. Emergency management records show that lead time was approximately 24 minutes. Post-event reviews by NOAA noted that storm organization and track changes occurred within a narrow time window. Detection and dissemination followed established procedures, but environmental changes developed faster than local response systems could accommodate. Operational reports emphasized that forecast guidance had correctly identified the regional threat. Precise impact timing and location could not be resolved until minutes before landfall. The difference between regional awareness and local consequence became visible in subsequent documentation. Similar timing gaps appeared during Hurricane Katrina's approach to the Gulf Coast in 2005. Forecast centers tracked the storm for several days as it crossed the Gulf of Mexico. Model projections increasingly favored landfall near southeastern Louisiana. Emergency bulletins were updated frequently. Evacuation recommendations were issued by state and federal agencies. Despite early forecasts, mandatory evacuation orders in parts of New Orleans were issued less than a day before landfall. Transportation agencies documented severe congestion on outbound routes. Public transportation capacity was limited. When levee failures occurred after landfall, floodwaters expanded rapidly. Congressional and FEMA investigations concluded that meteorological guidance was timely, but operational mobilization lagged behind environmental deterioration. Tornado outbreaks in the southeastern United States during April 2011 produced comparable patterns. Forecast offices had issued high-risk outlooks days in advance. Emergency managers were placed on alert. On April 27, storm cells formed and intensified across Alabama and neighboring states. Radar data shows that several tornadoes strengthened rapidly shortly before touchdown. Warning messages were transmitted according to protocol. Surveys conducted afterward found that repeated alerts throughout the day reduced urgency for some residents. In multiple communities, individuals delayed sheltering until visual confirmation was available. Weather Service reviews noted that storm evolution sometimes outpaced public reaction. Flood-related warnings also demonstrate narrow response windows. During prolonged rainfall along Colorado's Front Range in September 2013, weather stations recorded continuous precipitation over several days. River gauges showed steadily rising levels. Flash flood warnings were issued repeatedly as conditions worsened. In narrow canyons and foothill communities, water levels increased more quickly than expected. Several towns were isolated before evacuation advisories reached residents. State emergency management reports found that localized rainfall exceeded early projections. Terrain and soil saturation amplified runoff beyond modeled estimates. International events reveal similar dynamics. In western Japan during July 2018, a stationary weather front produced record-breaking rainfall. The Japan Meteorological Agency issued heavy rain warnings and evacuation advisories using standardized categories. Municipal governments relayed instructions through broadcast and mobile systems. In several districts, floodwaters reached residential areas before evacuation orders were fully implemented. Government reviews later concluded that warning terminology and timing did not align with the speed of river overflow in certain locations. Meteorological measurements were accurate, but communication intervals proved critical. Wildfire emergencies present related timing challenges. During the Camp Fire in California in 2018, strong winds and low humidity created extreme fire behavior. Fire weather watches and red flag warnings had been issued in advance. Utility and emergency agencies documented heightened risk conditions. After ignition, the fire spread rapidly toward populated areas. Evacuation notices were transmitted as conditions deteriorated. Road congestion and limited exit routes slowed departures. Investigative reports by CAL fire and state agencies determined that forecast information was correct, but the rate of fire expansion exceeded evacuation planning assumptions. In southeastern Australia, bushfires during the 2019-2020 season developed under severe heat and wind patterns. The Bureau of Meteorology issued extreme fire danger ratings. Emergency services used tiered warning systems to inform communities. Royal Commission findings showed that some areas were affected before highest level alerts were broadcast. Fire behavior intensified faster than anticipated in several cases. Infrastructure damage and power outages reduced the reliability of communication networks. Coastal hazards illustrate comparable limitations. When Typhoon Haiyan struck the central Philippines in 2013, storm surge heights exceeded earlier estimates. Meteorological agencies had issued warnings describing strong winds and coastal flooding. Many residents did not associate the term storm surge with rapid inland flooding. United Nations and government assessments found that although tracking data was accurate, terminology and public understanding limited effective response. Floodwaters reached residential zones within minutes in some areas. Heat emergencies also revealed delayed outcomes. During the Chicago heat wave of 1995, weather forecasts accurately predicted prolonged high temperatures and humidity. Heat advisories were issued. Public health agencies activated response plans. Mortality rates increased sharply over several days. Post-event studies found that many vulnerable individuals were isolated or unaware of risk severity. Weather information was available, but social and infrastructural factors slowed protective action. Modern alert systems rely on layered transmission. Weather offices issue warnings. Emergency management centers distribute messages. Telecommunications networks deliver notifications. Each stage introduces potential delay. Wireless emergency alerts, smartphone applications, and automated sirens have expanded reach. Reviews conducted after major disasters show that network congestion, device settings, and power failures can affect delivery. Messages may be issued promptly but received unevenly. Terminology also shapes timing. Watches, warnings, and advisories correspond to defined probability thresholds. Surveys conducted by NOAA and FEMA show that public interpretation varies. Some individuals delay action until conditions appear severe. During fast-developing events, forecasters may wait for confirmation before issuing high-level warnings. Internal guidance requires confidence in radar or observational signatures. Decision timelines are documented in forecast office logs. Emergency management agencies coordinate across multiple jurisdictions. Requests for evacuations, shelter activation, and transportation support require administrative steps. When environmental conditions evolve within minutes, these processes become visible in operational records. After-action reports routinely include comparative timelines showing storm development, warning issuance, and impact. These documents demonstrate that critical gaps often measure in minutes. In high-speed events, such intervals are operationally significant. Scientific journals analyze warning performance using statistical metrics such as lead time and false alarm rate. Long-term studies show gradual improvement in detection and dissemination. Progress varies by hazard type and region. Despite advances in observation and communication, warning systems remain dependent on interpretation and infrastructure. Radar imagery, satellite feeds, and surface measurements require evaluation before alerts are issued. Automation remains limited for complex scenarios. In mountainous, coastal, and densely populated regions, transmission delays are more common. Signal interference, damaged facilities, and overlapping jurisdictions affect timing. Over time, emergency archives accumulate detailed chronologies. Each incident produces a sequence of measurements, decisions, transmissions, and responses. These sequences are preserved in institutional records. They show that warnings are rarely absent. More often, they arrive close to the onset of impact. The interval between recognition and action remains narrow in many documented events. The documents maintain a consistent tone. Times and values are recorded. Procedures are referenced. Explanations remain technical. Responsibility is framed in operational terms. These records continue to guide training and revision. Agencies adjust protocols. Communication strategies are updated. Evaluation processes repeat after each major event. The structure of warning systems evolves incrementally. Their limitations remain documented in the same format as their successes. Movement altered by weather in ordinary spaces. Traffic and transportation records show that severe weather consistently changes how people move through public and natural environments. These changes are documented through highway sensors, transit logs, park permits, and emergency management reports. Unlike forecasts or warnings, movement data reflects how individuals and groups respond in real time. During Hurricane Harvey in 2017, rainfall in southeastern Texas exceeded 50 inches in some locations. Major highways in Houston and surrounding counties became impassable. The Texas Department of Transportation recorded more than 300 road closures within 3 days. Traffic cameras showed vehicles abandoning flooded routes. Public transit agencies suspended service across multiple districts. Ride-sharing companies released anonymized data showing sharp declines in trip completion and large increases in canceled rides. Emergency management reports noted that many residents attempted relocation after floodwaters had already begun rising. Evacuation routes became congested or blocked. Boat rescues increased as people became stranded in vehicles or homes. Movement patterns shifted from outbound evacuation to short-distance relocation within neighborhoods. Similar trends appeared during Hurricane Irma in 2017. Florida officials issued statewide evacuation orders. More than 6 million people attempted to leave coastal and low-lying areas. Gas stations ran out of fuel. Traffic volumes on Interstate 75 and Florida's Turnpike reached record levels. Transportation logs show that some evacuation routes slowed to less than 10 miles per hour for extended periods. Weather conditions deteriorated as storms approached. Rain bands and wind gusts affected visibility. Many evacuees altered routes or stopped moving entirely. Post-event studies found that late departures increased exposure to hazardous conditions. National parks maintain detailed records of visitor movement. During flash floods in Zion National Park in September 2015, entrance station logs and shuttle system data showed sudden changes in visitor distribution. Visitors concentrated near paved areas and shelters as storms developed. Trail usage declined sharply within 2 hours. Search and rescue reports indicate that several hikers were caught in narrow canyons after storms intensified. Stream gauges showed rapid water level increases. Park officials later noted that many visitors underestimated how quickly routes could become unsafe. In Yosemite National Park, winter storms regularly affect mobility. During January 2017, heavy snowfall closed major access roads, including Highway 120 and Highway 140. Park Service records show that visitor numbers dropped by more than 60% over 2 weeks. Snow accumulation exceeded 10 feet in some areas. Employees and residents relied on snow removal schedules and shuttle services. Supply deliveries were delayed. Rangers documented increased incidents of visitors becoming stranded between facilities. Movement patterns became limited to short, predictable routes. Urban transit systems record similar responses. During the January 2014 polar vortex, temperatures across the Midwest dropped sharply. In Chicago, commuter rail lines and buses experienced equipment failures. Train switches froze, service was reduced. Chicago Transit Authority reports show ridership declined by more than 20% during peak cold periods. Many commuters shifted to remote work or delayed travel. Emergency warming centers reported increased attendance as outdoor movement decreased. Flooding events also produced measurable shifts. During the September 2013 Colorado floods, highway closures isolated mountain towns. The Colorado Department of Transportation recorded over 400 miles of damaged roadways. GPS data from commercial trucking fleets shows major rerouting through neighboring states. Local residents relied on temporary bridges and airlifted supplies. Movement became dependent on emergency infrastructure rather than permanent networks. Travel times between nearby communities increased from minutes to hours. Wildfire emergencies demonstrate rapid movement changes. During the Camp Fire in 2018, evacuation routes in Paradise, California became congested within minutes. Cell phone mobility data later analyzed by researchers showed abrupt spikes in outbound movement followed by sharp declines as roads closed. Some residents altered routes multiple times as conditions changed. Others remained in place after becoming trapped by smoke and traffic. Fire behavior reports document how wind shifts affected road safety and evacuation feasibility. Maritime transportation is similarly affected. During Superstorm Sandy in 2012, ports along the East Coast were closed. The Port of New York and New Jersey suspended operations. Ferry services stopped. Vessel tracking systems recorded large-scale anchoring offshore. Cargo movement slowed. Supply chains experienced delays. Weather and Port Authority reports show that normal traffic patterns required weeks to recover. Air travel records provide additional evidence. During the February 2021 winter storm in Texas, airports in Dallas, Houston, and Austin canceled thousands of flights. Runways iced over. De-icing equipment was limited. Federal Aviation Administration data shows that regional flight networks were disrupted for several days. Passengers rerouted through distant hubs. Airport crowding increased as travelers waited for conditions to stabilize. Outdoor recreation data reflects weather-driven movement changes. During extreme heat in Death Valley in 2023, park officials closed several trails. Visitor counts dropped. Rangers reported that most activity shifted to early morning and evening hours. GPS-based fitness applications showed reduced daytime hiking activity. Heat advisories and trail closures directly influenced movement, timing, and route selection. Medical response reports documented fewer rescues during closed periods. International examples show similar patterns. During the 2021 floods in Germany, rail networks were damaged. Deutsche Bahn suspended service on multiple lines. Passenger flow data shows sharp reductions in regional travel. Bus services replaced rail where possible. Movement became localized. Emergency transport replaced routine commuting. Infrastructure damage reshaped daily mobility for months. Transportation researchers analyzed these shifts using anonymized mobile phone data, traffic sensors, and transit records. Studies published after major disasters consistently show that movement becomes more constrained, fragmented, and reactive under severe weather. Routes shorten, travel windows narrow, dependence on official guidance increases. Informal detours emerge. These changes are measurable and repeatable across events. Emergency management agencies incorporate movement data into planning models. Evacuation timing, shelter placement, and supply distribution depend on understanding how people actually move when conditions deteriorate. These datasets are preserved alongside meteorological and incident records. They provide a parallel account of how environmental change reshapes everyday behavior. The records remain descriptive, they chart distances, volumes, and delays. They do not assign motivation, they document how weather alters physical movement through shared spaces. Search operations constrained by environmental instability. Search and rescue agencies document weather conditions as a central operational variable. Mission reports, deployment logs, and after-action summaries consistently record how wind, precipitation, temperature, and terrain affect access and visibility. These records show that unstable weather often determines the pace and scope of organized searches. During the disappearance of 6-year-old Dennis Martin in Great Smoky Mountains National Park in 1969, weather conditions repeatedly disrupted search efforts. Park records and National Weather Service data show that thunderstorms, fog, and heavy rainfall developed shortly after the child was last seen. Streams flooded. Visibility declined across ridgelines. Helicopter operations were suspended for extended periods. Ground teams reported limited progress due to wet terrain and cloud cover. Despite one of the largest search efforts in park history, the child was never located. Mountain rescue operations frequently encounter similar constraints. In 1995, climber Allison Hargreaves disappeared on K2 in Pakistan during deteriorating weather. High winds and snowfall made ascent and descent routes unsafe. Rescue attempts were delayed and eventually halted. Expedition reports and meteorological data confirm sustained storm conditions at high altitude. No recovery was possible. In national parks, rapid weather changes often interrupt organized searches. During the disappearance of Bill Owasco in Joshua Tree National Park in 2010, search teams operated under extreme heat. Temperatures regularly exceeded 100 degrees Fahrenheit. National Park Service records show that air operations were limited by thermal turbulence. Ground teams required frequent rest periods. Search duration was shortened to prevent heat-related injuries. Owasco's remains were found in 2018, 8 years later, in an area that had been previously searched under more limited conditions. Flood events also restrict search activity. During the September 2013 Colorado floods, emergency agencies conducted dozens of missing person searches in mountain communities. Swift water conditions prevented entry into canyons and riverbanks. Helicopters were grounded by low clouds and heavy rain. State emergency management reports document repeated mission suspensions due to unsafe conditions. Some searches resumed only after water levels receded. Maritime search operations depend heavily on weather stability. When Malaysia Airlines Flight 370 disappeared in 2014, large-scale searches were conducted in the southern Indian Ocean. Meteorological and oceanographic conditions included strong winds, high waves, and shifting currents. Search vessels were forced to alter routes repeatedly. Sonar surveys were delayed by sea state. Official investigation reports describe frequent weather-related interruptions affecting search accuracy and coverage. In Arctic and subarctic regions, cold and wind present additional barriers. During the search for missing hunter Geraldine Largay on the Appalachian Trail in Maine in 2013, teams operated under cold, wet conditions. Fog and rain reduced aerial visibility. Dense vegetation and wet ground slowed movement. Maine Warden Service reports show that several planned search phases were postponed due to storms. Largay's remains were located in 2015, less than 2 miles from the trail. Avalanche risk further complicates alpine searches. In February 1999, multiple skiers were buried in avalanches in Galtour, Austria. Rescue teams faced ongoing snow instability and additional slide risk. Weather records show heavy snowfall and strong winds preceding the event. Search operations were repeatedly halted for safety assessments. Some recoveries were delayed for weeks. Desert environments impose different limitations. During searches for missing hikers in Death Valley and Mojave Desert regions, extreme heat and windstorms reduce visibility and endurance. Bureau of Land Management and National Park Service reports show that sandstorms and heat waves frequently suspend flight operations. Equipment failure rates increase under high temperatures. Search grids must be modified to reduce exposure. Wildfire conditions also restrict rescue activity. During the 2021 Dixie Fire in California, several missing person searches were suspended due to smoke density and fire spread. CAL FIRE incident reports indicate that air support was limited by visibility and heat. Ground teams were redirected to evacuation and protection duties. Some searches resumed only after containment improved. Modern search operations rely on layered resources. These include helicopters, drones, canine units, GPS tracking, and satellite imaging. Each tool has weather limitations. Drones cannot operate safely in high winds. Dogs lose scent in heavy rain. Thermal cameras perform poorly in extreme heat. Satellite imagery may be obstructed by cloud cover. Search coordinators document these constraints in operational logs. Mission planning sheets often include weather thresholds for deployment. When conditions exceed these limits, operations are delayed or scaled back. These decisions are recorded without commentary. Federal agencies such as the National Park Service, Coast Guard, and state search units publish annual summaries. These reports consistently list weather as a primary limiting factor. Delays are measured in hours, days, or seasons. Winter searches in mountainous regions are often suspended until spring melt. Floodplain searches may wait for water levels to stabilize. Academic studies of search effectiveness confirm these patterns. Research published in journals such as Wilderness and Environmental Medicine and Search and Rescue International Review shows that detection probability declines sharply under poor weather conditions. Visibility, terrain stability, and responder fatigue are identified as key variables. Technological advances have expanded operational capacity. All-weather helicopters, improved forecasting tools, and satellite communication systems have increased reach. Despite this, fundamental physical limits remain. Wind, water, heat, and cold continue to restrict access. After-action reviews rarely attribute failure to personnel. Instead, they reference environmental constraints, unsafe conditions, or operational risk. These phrases appear repeatedly in official documents. Over time, institutional archives accumulate detailed weather-linked timelines. Each search includes temperature readings, wind data, and precipitation totals alongside personnel assignments and coverage maps. These datasets form parallel records of environmental and human activity. They show that search operations are shaped as much by atmospheric conditions as by available resources. Movement, detection, and recovery remain dependent on stability that cannot always be achieved. The records remain factual and restrained. They list what could be done and what could not. They preserve measurements and decisions without interpretation. Delayed discoveries after landscapes were altered. Changes in terrain caused by weather and seasonal cycles often affect when and where missing persons are eventually located. Snow accumulation, spring melt, erosion, flooding, and vegetation growth can conceal or expose physical evidence. Law enforcement agencies, park services, and forensic teams document these changes in recovery reports and investigative summaries. In May 2010, experienced hiker and former park ranger Bill Ewasco disappeared in Joshua Tree National Park. Initial searches covered large areas under extreme heat. Despite extensive ground and air operations, no trace was found. Over the following years, seasonal winds and erosion gradually shifted surface material in remote desert terrain. In January 2018, human remains and personal items were discovered in a rocky wash less than 2 miles from a trailhead. National Park Service reports noted that earlier searches had passed nearby, but terrain features and debris had limited visibility. Snow cover plays a similar role in mountainous regions. In April 2015, a skier went missing near Crystal Mountain in Washington state after leaving marked runs. Search teams suspended operations because of avalanche risk and heavy snowfall. The area accumulated several meters of snow over the winter. When snow melted in late summer, remains were discovered in a steep drainage channel. Sheriff's Office records confirmed that the location had been inaccessible during earlier searches. Seasonal melt has also affected long-term cases in high-altitude regions. In 2013, the remains of mountaineer Rob Hall, who died during the 1996 Mount Everest disaster, were located after being hidden for years beneath ice and snow. Climbers reported that glacier movement and melting exposed equipment and remains previously buried. Similar recoveries have occurred on other Himalayan peaks as shifting ice alters surface conditions. Flooding frequently reshapes riverbanks and low-lying terrain. After Hurricane Katrina in 2005, extensive flooding altered neighborhoods in New Orleans and surrounding parishes. Debris, sediment, and collapsed structures covered large areas. Over the following months, recovery teams located remains in places that had been submerged or obstructed. Federal and state investigative reports describe how receding waters revealed locations that had been unreachable during the initial response. In September 2013, severe flooding in Colorado caused landslides and riverbank erosion throughout mountain valleys. Several missing persons were not located during active search periods. As water levels receded and sediment shifted, remains and personal items were discovered months later along altered channels. Geological surveys documented changes in river paths and slope stability that affected recovery timelines. Vegetation growth can also delay discovery. In forested environments, dense foliage and fallen trees reduce visibility from both the ground and air. During the search for Geraldine Largay on the Appalachian Trail in Maine in 2013, teams encountered thick brush, wet ground, and limited sightlines. Despite extensive coverage, her campsite remained undetected. In 2015, her remains were found less than 2 miles from the trail. Warden Service reports concluded that vegetation, density, and terrain features had concealed the site. Coastal environments are shaped by tides, currents, and storms. In 2014, a kayaker went missing near Half Moon Bay, California. Initial searches were affected by high surf and unstable shoreline conditions. Over time, winter storms altered beach profiles and redistributed sand. Several months later, personal equipment was recovered along a newly exposed section of shoreline. Coast Guard reports noted that sediment movement influenced the timing of recovery. Glacial and permafrost regions show long-term effects. In the Alps, multiple climbers from earlier decades have been recovered as glaciers retreat. In 2017, the remains of a German couple who disappeared in 1942 were found on the Glacier des Bossons in Switzerland. Melting ice exposed preserved clothing and documents. Swiss authorities confirmed that glacier shrinkage revealed the site. Similar discoveries have occurred in Alaska. On Denali, formerly Mount McKinley, melting snowfields and shifting ice have exposed equipment and remains from expeditions dating back several decades. National Park Service studies document how temperature increases and reduced snowfall alter long-term recovery patterns in high-altitude areas. Urban environments are also affected by weather-driven change. After major storms and floods, debris, removal, and reconstruction projects frequently uncover evidence. Following Superstorm Sandy in 2012, demolition and sediment clearing in parts of coastal New Jersey and New York revealed vehicles and personal items linked to missing persons. Police and municipal reports describe how rebuilding created new access points. Drought produces the opposite effect by reducing water coverage. In 2022, declining water levels at Lake Mead exposed multiple sets of human remains. Investigators determined that some dated back several decades. The Bureau of Reclamation confirmed that reduced reservoir levels had uncovered previously submerged areas. Similar discoveries have occurred at other reservoirs during prolonged dry periods. Search agencies track environmental change through mapping and monitoring. Satellite imagery, aerial surveys, and geological assessments are used to identify areas likely to shift over time. These tools are often applied years after formal searches have ended. Recovery reports frequently reference environmental exposure or terrain alteration as contributing factors. These terms appear in police, park service, and forensic documentation. They indicate that discovery occurred only after physical conditions changed. Scientific studies support these observations. Research in forensic geography and wilderness search theory shows that terrain modification affects detection probability. Snowpack depth, erosion rates, vegetation density, and water flow are measured as operational variables. Despite advances in technology, many areas remain inaccessible during certain seasons. Winter closures, flood stages, and fire restrictions delay re-entry. Searches resume only when conditions stabilize. As a result, discovery timelines often extend far beyond initial investigations. Months or years may pass before landscapes reveal what had been hidden. These outcomes are documented without interpretation. Institutional records preserve original search maps alongside later recovery locations. Comparisons show how terrain evolution altered visibility and access. These materials remain part of permanent case files. They reflect how natural processes continue after formal searches end. Weather reshapes environments independently of investigative schedules. Evidence emerges according to physical cycles rather than administrative timelines. The documentation remains factual. Dates, coordinates, and environmental conditions are recorded. No additional meaning is assigned beyond measurable change. Records preserved without resolution. Weather agencies, law enforcement departments, park services, and emergency management offices maintain extensive archives documenting environmental conditions and missing person cases. These records are stored in databases, printed files, and digital repositories. They include forecasts, station readings, dispatch logs, search maps, and investigative summaries. Over time, these materials accumulate into parallel systems that rarely intersect beyond shared timestamps and locations. The National Oceanic and Atmospheric Administration maintains climate and weather archives dating back more than a century. These include surface observations, satellite imagery, radar records, and storm reports. Each entry is tagged with coordinates and time markers. Data is standardized to allow long-term comparison. Extreme events, unusual patterns, and short-term anomalies are preserved without narrative interpretation. Law enforcement agencies maintain separate missing person databases. In the United States, the National Crime Information Center stores active and historical reports. The National Missing and Unidentified Persons System, known as NAMAS, links case files, dental records, and forensic data. Entries include last known locations, physical descriptions, and investigative notes. Weather information is occasionally referenced but remains secondary. Park services and wilderness agencies keep independent records. The National Park Service archives search and rescue mission reports for each park unit. These documents include weather conditions, personnel deployment, coverage zones, and termination decisions. Similar systems exist in state parks and forest services. Reports are written in standardized formats to ensure consistency across regions. Coast Guard and maritime authorities maintain their own archives. Incident logs, vessel tracking data, and weather buoy readings are stored together for review. Search patterns, fuel consumption, and sea state conditions are documented in detail. These records remain accessible for future reference and training. Emergency management agencies collect additional layers of information. Situation reports, evacuation timelines, shelter occupancy records, and infrastructure damage assessments are compiled after major events. These materials are submitted to state and federal repositories. Weather data is included as background context rather than a primary variable. Academic institutions also maintain independent datasets. Universities and research centers store long-term climate records, disaster response surveys, and satellite analyses. These collections are used for statistical studies and model evaluation. Individual missing person cases are rarely examined directly within this research. In many systems, files remain open for years. Unresolved cases are reviewed periodically, often when new technology becomes available. DNA databases, facial reconstruction software, and geographic profiling tools are introduced into older investigations. Weather archives are consulted primarily to reconstruct timelines. Cross-referencing between agencies is limited. A Park Service report may reference a Sheriff's Office case number. A Coast Guard file may cite National Weather Service station data. These links are functional rather than analytical. Databases are designed for retrieval, not interpretation. Digitization has expanded access. Paper records from earlier decades have been scanned and indexed. Newspaper archives, police blotters, and meteorological logs are searchable online. Researchers and journalists can access multiple systems independently. Integration between platforms remains partial. NamUs and similar systems allow public searches. Families, volunteers, and investigators review entries for possible matches. These searches focus on physical characteristics and geographic proximity. Weather patterns are rarely used as primary filters. Meteorological archives are structured differently. Data is stored in continuous time series. Researchers analyze trends, averages, and deviations. Individual human outcomes are not included in these datasets. Storm events are categorized by intensity, duration, and impact metrics. After-action reviews sometimes attempt limited integration. Following major disasters, agencies compile joint reports combining weather, response, and casualty data. Examples include post-Katrina reviews, wildfire investigations, and flood assessments. These reports focus on institutional performance rather than unresolved disappearances. International systems operate in similar ways. The United Kingdom's Met Office, Japan Meteorological Agency, and European Center for Medium-Range Weather Forecasts maintain independent climate archives. Police agencies in those countries maintain separate missing person registries. Data sharing occurs mainly during active investigations. Over time, these systems expand. Storage capacity increases, resolution improves, metadata becomes more detailed. Despite these changes, the basic structure remains consistent. Environmental records and investigative records remain parallel. Researchers studying disaster outcomes rely on aggregated statistics. Fatality counts, injury rates, and economic losses are correlated with storm intensity and warning lead time. Unresolved cases are usually excluded from these analyses due to incomplete data. Forensic specialists occasionally revisit older files. Advances in isotope analysis, satellite imagery, and terrain modeling have been applied to cold cases. Weather data may be consulted to reconstruct conditions at specific times. These efforts depend on the quality and completeness of archived material. Government audits regularly evaluate data retention practices. Reports emphasize accuracy, redundancy, and security. Agencies are required to preserve records for defined periods. Some materials are retained indefinitely. Public access policies vary. Certain documents are restricted due to privacy laws. Others are released through freedom of information requests. Weather records are generally open. Investigative files are often partially redacted. The result is a distributed archive system. No single institution maintains a complete picture. Each agency preserves its own version of events. Overlapping timelines exist, but interpretation is left to later users. These archives grow through routine operations rather than special effort. Every forecast update, search, deployment, and case entry adds to the record. Most entries are never revisited. They remain available for reference, comparison, and verification. They do not generate conclusions. They provide structured memory without narrative resolution. Measurements, coordinates, and timestamps form the core of these systems. Human outcomes are recorded in separate formats. The two coexist without formal integration. This separation defines how information persists. Weather is stored as data, disappearances are stored as cases. Both remain active within their own institutional frameworks. Case reviews conducted years after initial closure. Law enforcement agencies periodically reopen or reassess unresolved disappearance cases as part of routine review programs. These efforts are documented through internal audits, cold case units, and special investigative task forces. The purpose is to determine whether advances in technology, newly available records, or overlooked details warrant renewed attention. Weather-related information is often re-examined during these reviews. Many police departments maintain formal cold case divisions. These units focus on cases that remain unsolved after extended periods, often 5 years or more. Files are digitized, evidence inventories are updated, and witness statements are rechecked. Archived weather reports are frequently included in case materials to reconstruct conditions at the time of disappearance. In national parks, similar review processes are carried out by ranger services and investigative branches. When a missing person case remains unresolved, park authorities periodically reassess search records and environmental data. These reviews rely on original mission reports, GPS tracks, and station readings. Weather information is used to verify access limitations and visibility conditions. The Federal Bureau of Investigation participates in selected long-term reviews, particularly when federal land or interstate activity is involved. Case files may be transferred between agencies for evaluation. In these exchanges, meteorological records are preserved as part of the original timeline. They are not revised unless errors are identified. One example of systematic review occurred after the establishment of the National Missing and Unidentified Persons System. Law enforcement agencies were encouraged to upload older case files into a centralized platform. This process required standardization of information, including environmental conditions. Archived weather data was cross-checked with case timelines to ensure accuracy. Forensic laboratories also contribute to long-term reassessments. Advances in DNA analysis, isotope testing, and material degradation studies allow previously unusable samples to be re-examined. When remains or belongings are recovered years later, environmental exposure is evaluated using historical climate records. In coastal regions, sheriff departments and Coast Guard units periodically review unresolved maritime disappearances. Vessel tracking data, buoy records, and storm reports are reanalyzed. These reviews aim to determine whether updated ocean current models or wind reconstructions provide additional context. Mountain rescue organizations maintain similar archives. The Mountain Rescue Association in North America keeps detailed records of unsuccessful searches. These are reviewed during training and certification processes. Weather conditions are examined to understand why certain areas could not be accessed at specific times. State-level emergency management agencies conduct periodic audits of disaster-related missing person cases. Following hurricanes, floods, and wildfires, unresolved files are reviewed alongside infrastructure and evacuation records. These audits focus on procedural compliance rather than case resolution. In the United Kingdom, police forces use major incident review teams to reassess complex or long-standing cases. These teams examine original command logs, witness interviews, and environmental reports. Weather information is used to verify travel conditions and terrain accessibility. Japanese police follow similar practices through prefectural review boards. Cases involving mountain accidents, coastal disappearances, or flood-related incidents are periodically reassessed. Meteorological agency data is included in these reviews to confirm historical conditions. Re-evaluation processes are governed by formal guidelines. Investigators follow structured checklists that include evidence handling, data completeness, and documentation quality. Weather data is reviewed for consistency with reported movements and search activities. Technological changes have expanded review capabilities. High-resolution satellite imagery, improved terrain modeling, and digital mapping allow older search areas to be reassessed virtually. Analysts can overlay historical weather data onto modern maps to examine exposure patterns. Despite these tools, most reviews result in no new findings. Internal memoranda frequently note that all available evidence has been exhausted. Environmental limitations documented in original reports remain unchanged. Funding and staffing constraints influence review frequency. Cold case units operate with limited resources. Priority is often given to cases involving new leads or public safety concerns. Weather-related disappearances are typically reviewed only when new physical evidence emerges. Families of missing persons may request formal case reviews. These requests are logged and evaluated by supervisory staff. Agencies respond by summarizing existing records, including environmental factors. Reopened investigations are rare and require documented justification. Court rulings and policy changes can also prompt reevaluation. New standards for evidence handling or data retention may require older files to be updated. During these processes, archived weather records are verified against modern databases. Academic researchers occasionally participate in long-term reviews, particularly in wilderness and disaster-related cases. Universities collaborate with agencies to study search outcomes and environmental constraints. These projects focus on improving future operations rather than resolving specific cases. International organizations provide additional frameworks. Interpol issues guidelines for long-term missing person investigations, emphasizing record preservation and periodic reassessment. Environmental data is identified as a supporting element. Review findings are usually recorded in internal reports. These documents summarize what was examined, what was confirmed, and what remains unknown. They do not reinterpret events beyond documented evidence. Most reviewed cases retain their original status. Files are returned to inactive or dormant categories. Updates are entered into databases, and review dates are logged. These reassessment processes create secondary layers of documentation. Original reports are preserved alongside later evaluations. Together, they form extended administrative histories. The structure of these records emphasizes continuity rather than resolution. Each review adds technical annotations without altering conclusions. Weather data remains fixed within these timelines. Over time, repeated reviews demonstrate the limits of retrospective investigation. Environmental conditions, once recorded, cannot be reconstructed beyond available measurements. The documentation remains factual. It reflects institutional efforts to maintain accuracy and accountability. It does not generate explanatory narratives. Case reviews continue as part of standard practice. They ensure that unresolved files remain verifiable and complete. They preserve records for future reference. Uncertainty maintained through administrative process. When a disappearance remains unresolved after formal investigation and search operations, it enters a long-term administrative phase. During this period, responsibility shifts from active response units to records, divisions, supervisory offices, and centralized databases. The case becomes part of an institutional system designed to preserve information rather than pursue continuous inquiry. In most jurisdictions, unresolved files are transferred from investigative teams to archival management units. These units verify that reports, evidence, inventories, and correspondence are complete. Digital copies are created if paper records exist. Metadata is added to indicate status, jurisdiction, and review history. From that point forward, the file is maintained through standardized procedures. Law enforcement agencies rely on case management software to track unresolved entries. Each file is assigned identifiers that allow retrieval by name, date, or location. Changes to status require supervisory approval. Routine access is limited to authorized personnel. The system prioritizes consistency over reinterpretation. Park services and wilderness authorities apply similar processes. Once search termination reports are approved, supporting materials are transferred to permanent storage. These include maps, GPS tracks, radio transcripts, and weather summaries. Reassessment is permitted only under defined conditions, such as discovery of physical evidence or confirmed sightings. Maritime agencies preserve unresolved incidents within vessel and casualty registries. Position data, drift models, and weather buoy records remain attached to each file. When recovery efforts are suspended, the administrative classification changes, but the underlying documentation remains intact. International agencies operate under comparable frameworks. Police departments in Europe, Asia, and Australia maintain unresolved files according to national retention laws. Interpol guidelines emphasize preservation, verification, and restricted access. Cross-border coordination occurs only when new evidence emerges. These systems are designed to prevent data loss and unauthorized modification. Audit trails record every access and update. Backup copies are stored in multiple locations. Migration to new platforms occurs according to scheduled cycles. The structure limits interpretive activity. Investigators reviewing older cases are required to rely on original documentation. Speculation is discouraged. Findings must be supported by verifiable records. Weather data remains fixed unless official corrections are issued by meteorological agencies. Periodic reviews are conducted primarily for administrative purposes. Supervisors confirm that files meet regulatory standards. Evidence retention policies are checked. Privacy compliance is verified. These reviews rarely alter case status. Legal proceedings may introduce limited changes. Courts may issue declarations of death after extended absence. These rulings update civil records and insurance documents. Law enforcement files remain classified as unresolved unless remains are identified. Public access to these records is regulated. Freedom of information laws allow limited disclosure. Sensitive details are redacted. Weather data is usually released in full. Investigative notes are often restricted. Media inquiries are processed through designated communication offices. Agencies provide factual summaries based on existing files. No new interpretation is added. Statements are reviewed for compliance with policy. Technological advances have expanded analytical capacity. Geographic information systems, satellite archives, and climate databases allow retrospective reconstruction of conditions. These tools are used selectively. Their results are appended to files without replacing original data. Forensic improvements occasionally lead to updates. DNA identification, isotope analysis, or material testing may link remains to existing cases. When this occurs, records are amended. The administrative phase ends only when confirmation is achieved. Most unresolved cases do not reach this stage. They remain inactive for decades. Their presence in databases becomes part of statistical background rather than operational focus. Families and representatives may request reviews. Agencies respond by restating documented facts. Unless new evidence is presented, administrative status remains unchanged. Training programs incorporate unresolved cases as procedural examples. Instructors use archive materials to illustrate documentation standards, search planning, and termination criteria. The emphasis remains on process. Budgetary constraints also shape long-term handling. Cold case units prioritize cases with recent leads. Weather-related disappearances without new information are rarely reassigned. The result is a stable administrative category. Files are preserved, indexed, and protected. They exist within systems optimized for accuracy and continuity rather than resolution. Weather archives continue to develop independently. Climate databases expand, forecast models improve. These developments do not retroactively alter investigative records. Institutional responsibility is expressed through maintenance rather than action. Agencies ensure that information remains accessible, verifiable, and secure. Over time, unresolved cases become reference points. They appear in audits, reports, and statistical summaries. Their individual details remain unchanged. The systems that preserve them operate quietly. They function through routine updates, backups, and compliance checks. No narrative is constructed beyond recorded facts. This administrative structure defines how uncertainty is managed. It does not resolve absence. It documents it. Each file represents a completed sequence of response, search, and review. What remains is an organized record of what was observed, attempted, and confirmed. Weather data, movement logs, and operational reports remain attached to these files. They provide context without explanation. The case remains present within institutional memory through documentation alone. It persists through regulation, storage, and verification. It remains unresolved, not through neglect, but through formal process. If you found this video interesting, subscribe for video like this. Share it with someone who loves hiking and the outdoors. Let me know your thoughts in the comments, and I'll see you in the next one.